Hi everyone, in this video I will be talking about iron deficiency anemia. I will give you a proper introduction about iron deficiency anemia and how iron absorption occur, how the metabolism of iron is regulated and so on, because that is required for you to understand the diagnosis of iron deficiency anemia. So let's begin. First of all, we will talk about what is anemia. So it is the decrease in the red cell circulatory mass well below the normal limits with respect to an age group, sex, or and geographical region. So when red cells in our body are decreased below the normal limits, and that too with respect to a proper age group, because with an age group, sex, or geographical region, the level of RBCs or the range of hemoglobin varies, the normal range of hemoglobin. If I talk about an adult male, then there the normal range of hemoglobin is different. If I talk about an infant, then the normal range of hemoglobin is different. And with sex also it varies, because in females normally they have a lower range of hemoglobin because they are having menstruation. And if I talk about the geographical region, then obviously a person living on mountain will have a different range of hemoglobin with respect to a person living somewhere else or living on the plains, because there is compensatory increase in the number of RBCs for a person living on mountain. So this line is very important and has to be added in the definition of anemia. Now if I talk about iron deficiency anemia, then it is the anemia caused due to the depletion of iron in the body, leading to inadequate hemoglobin synthesis. So basically when iron is less in the body, then that is leading to the inadequate synthesis of hemoglobin, which is required by the RBCs to transport oxygen, and also the formation of RBCs, because erythroblasts require iron to form hemoglobin and produce hemoglobin in the RBC. So when inadequate hemoglobin is not being formed, also the erythroblasts will also not multiply that much. So that is a very big problem. Also, it is the most common nutritional disorder occurring in the world, and also the most commonly occurring anemia. So this line is also very important, that in clinics you will most frequently see that the etiology of anemia is iron deficiency. So, what is the etiology of iron deficiency anemia, or why does it occur? What are the causes? So, basically, if a person, first of all, and the most important cause is the lack in diet, that person is not taking adequate iron in the diet. He or she is a teenager, he or she eats junk food, and they are not taking consuming animal products due to some other reasons like meat, milk, eggs. So that can cause iron deficiency anemia. Or if there is chronic blood loss which is occurring for a very long period of time but has gone unnoticed. In a menstruating lady, if she's losing blood for she's losing blood every month. So, and if she is not taking the adequate amount of iron in her diet, then that can cause iron deficiency. If there is internal hemorrhage in the body cavity, for example in the GIT or in different organs, which is going unnoticed, then that can also cause iron deficiency anemia. Or if there is increased demand, for example in a pregnant lady, her fetus requires iron for the synthesis of hemoglobin too. So now we have two people, the pregnant lady also and the fetus also. So there is increased demand, and if this demand is not met, then that can also cause iron deficiency anemia. If I talk about inadequate absorption, that iron is being not absorbed properly, so that can be seen in cases of intestinal sprue or gastrectomy. Now in intestinal sprue, there is loss of duodenal mucosal cells, then that can lead to decreased absorption of iron, because duodenal mucosal cells are involved in the absorption of iron. And in gastrectomy, there is decreased secretion of HCl or hydrochloric acid. So hydrochloric acid is required for converting Fe3 plus to Fe2 plus, and this Fe2 plus is what is absorbed in the GIT. So when this process will not occur, then most of this inorganic iron will be lost in the feces and it will not be absorbed. So this can lead to iron deficiency anemia. Now if I talk about iron metabolism, then iron metabolism, the source is, first of all, what is the source of iron? Then, like I told you, animal products and leafy vegetables, and it is present in two forms in our diet: heme iron and non-heme iron. So heme iron is the one which is majorly present in our diet, and non-heme iron is the inorganic iron called the Fe3 plus or Fe2 plus. About 20% of the total heme iron is very easily absorbable. In contrast, only 1 to 2% of the inorganic iron or the non-heme iron is only absorbable. For example, if the total heme iron is for say 100 milligrams, then only 80, then out of that 20% or 20 milligrams is easily absorbed. Rest 80 will be excreted. But in case of inorganic iron, if I give a person inorganic, if in the diet the inorganic form of iron is given, then only 1 to 2% is absorbed readily. Now I will give the explanation of why this happens later. A normal Western diet has 10 to 20 milligrams of iron, and the demand of for iron in an adult male and female is 8 milligrams and 18 milligrams respectively. So in an adult male, generally in females there is increased requirement of iron because she is losing blood in menstruation, so we have to supply more iron to her in response for menstruation. And a Western diet has 10 to 20 milligrams of iron, so that covers for the does not cause the lack of iron in our body. If I talk about total body iron, then there are two types of two forms of total body iron. First one is the storage form, or storage, as the word suggests, that the iron is stored in this form, and the functional form in which the iron is being used in different molecules for carrying out necessary functions of our body. So the storage form is present as ferritin or hemosiderin, and the functional form is also the major form in our body, of which 80% is found in the hemoglobin. This line is very important. The functional form is the major form of total body iron. The storage form is only 10 to 15%, but out of the functional, the 80% of the functional form is hemoglobin. And as you know that hemoglobin is involved in the transportation of oxygen in our body. And then there's rest of the functional form is found in myoglobin, which is an enzyme, and the cytochrome enzymes, which are involved in the detoxification of drugs, and you will read about it in pharmacology. And myoglobin, which stores oxygen in our muscles. So these are all the functional forms of hemoglobin, and this ferritin or the hemosiderin is the storage form of hemoglobin, and this is present in the hepatocytes and the mononuclear phagocyte system, which is present in the spleen, liver, and bone marrow. All the mononuclear cells which are present in the spleen, liver, or the bone marrow, total all of them are together referred to as the mononuclear phagocyte system. Now the iron is continuously recycled between the functional and storage pools. This line is very important. Now how does it occur? So basically iron is absorbed from the intestine, and then from the intestine this iron binds to a protein in the plasma called transferrin. Now this transferrin is what transports iron to different parts of our body. So it goes to the marrow, to the erythroblasts, and there the erythroblasts have a transferrin receptor. This red one here is a transferrin receptor, and the transferrin receptors bind to the transferrin molecule containing iron, and this is then internalized and iron is released, and then the erythroblasts utilize it to produce erythrocytes containing adequate hemoglobin. And the circulating erythrocytes, when they die out after 120 days, then they are consumed by the macrophages, and these macrophages, they eat the RBCs, degrade the hemoglobin, and release the iron. Now this iron is stored in the form of ferritin in the macrophages, and some of it is also released in the iron form, which binds to transferrin, and again this cycle occurs. Now some of this transferrin also transferrin bound to iron also goes to the skin, gut, and endometrium, or the mucosal cells, where these mucosal cells after some days are shed, and this is how per day we lose 1 to 2 milligram of iron. So that is how the absorption and the excretion of iron occurs in our body. And also this transferrin also binds to the transferrin receptors present on hepatocytes, where again the iron is stored as ferritin or hemosiderin, the storage form of iron. And the ferritin molecules are proteins which are found in the cytosol of hepatocytes and macrophages, and when these ferritin molecules become excess or they start aggregating, then they form hemosiderin. Now hemosiderin is present in a very lower amounts in cell, in the cytosol of cells in normal conditions, but in hemolytic anemias, this hemosiderin molecules, they are found abundantly, and you can visualize them by using Prussian Pearl's Prussian stain. Now let's talk about iron absorption and how this absorption is regulated. So in a normal person, the food iron, as you know, it contains the heme iron and the non-heme iron. Now the non-heme iron contains majorly Fe3 plus. That is why you see only 1 to 2% is readily absorbable, because first of all this Fe3 plus has to be converted to Fe2 plus by the luminal enzyme called duodenal cytochrome B, and heme iron is readily absorbed by the heme transporter. So that is what causes this increased difference between the numbers or the percentages between heme iron and non-heme iron. Now this heme iron, this releases Fe2 plus, and this again this Fe2 plus is released here. Now some of this Fe2 plus is stored as ferritin, but in a normal person some of this also goes out through ferroportin, a protein which allows the export of Fe2 plus ions. And outside, since this Fe2 plus ions can't be present freely in the, you can't release ions in the blood freely, because ions are highly reactive and they can bind to different certain proteins and cause their denaturation. So this first is converted by hephastatin, again which is a receptor and an enzyme both, and this converts the Fe2 plus to Fe3 plus. And now this Fe3 plus binds to our transferrin molecule which is present in the plasma, and then it is transported to different organs like liver and the erythroid marrow which require it. Now according to the iron transport or the amount of iron which reaches the liver releases the hormone hepcidin, and this hepcidin then causes or regulates the iron metabolism, iron absorption. How does it regulate? Then the plasma hepcidin, it causes the degradation of ferroportin, this protein. So normally in a normal person the levels of hepcidin are normal, they are neither to increase nor to decrease. So this balance is maintained and the iron absorption is normal. Now in a person who is having low plasma iron, or the iron stores are less, or either there is ineffective erythropoiesis, and due to this ineffective erythropoiesis there is increased demand of iron, or during in the situations of hemochromatosis, what happens that, as you know, that the total plasma iron is less, then this is sensed by the liver, and in response to that it releases less amount of hepcidin, because the plasma stores of iron are less. So when this less amount of hepcidin is secreted, then this ferroportin molecule is not degraded. Now since this ferroportin molecule is not degraded, this Fe2 plus is exported outside, and a lot of Fe2 plus is exported outside, and this Fe2 plus then converts to Fe3 plus, and then so on, it binds to transferrin and goes to different organs. So and then the low plasma iron demand is met through this. And in cases where there is high plasma iron, or in cases of systemic inflammation, as you know, in inflammation signals liver to produce increased amount of hepcidin. Basically it's a acute phase reactant, it is a positive acute phase reactant which is increased in cases of inflammation. So when there is high plasma hepcidin, then there is increased destruction of ferroportin, and due to the destruction of ferroportin, the Fe2 plus which is present in the mucosal cells, they are only stored as ferritin and they are not exported out. Now what happens to this ferritin which is stored in the mucosal cells? Now these mucosal cells will shed out because they are epithelium. So when they are shed out, this iron is also lost. So that is how this high plasma iron starts decreasing, or the compensatory response occurs due to this high plasma iron. Now I want to add one more thing, that this ferroportin is not only present in mucosal cells, it is also present in the macrophages, and its production is regulated by hepcidin. So in the cases of systemic inflammation, these macrophages, they start accumulating ferritin, because since ferroportin is being degraded, hepcidin also acts on them too. So hepcidin is being degraded, so they start accumulating ferritin inside them. And that is why in chronic inflammation you will see that when total serum ferritin is taken, then the ferritin levels are increased in the body. Why so? Because ferroportin is being degraded, so macrophages can't send them out. Like here, when they degrade the RBCs, they store the Fa2 plus in form of ferritin, but they also send some out. But when the hepcidin level is high, the ferroportin is being degraded. They can't send the iron out, so it is being accumulated in the ferritin molecule. That's how the absorption, metabolism, and the regulation of iron absorption occurs in the body. I have explained you the normal physiology. We'll talk about even more different conditions, but the basics have been given by me so that you can understand the diagnosis of iron deficiency anemia and different conditions involving iron like hemochromatosis and different hemolytic anemias. So in the next video I'll talk about the pathogenesis, the clinical features, and how we diagnose iron deficiency anemia. So if you like this video, give a thumbs up, comment down the comment section, and please subscribe. It motivates me to produce more videos. I will see you in the next one. Till then, bye bye.